how many of you have used any kind of speech-to-text engine before? Using Google Cloud or your mobile for typing, those kind of things. Right, a lot. So what DeepSpeech is it's a open source end-to-end speech recognition engine which will run completely in your device, that be a mobile or laptop, without any internet connection. So all the models of speech recognition, everything will be in the device. I will show a little bit about how you can use that, but you have a lot of information available already in the internet. What I really want to talk about today is how it actually works in the back end. What goes on, what are the architecture changes which has been done to make it work, and what is generally the architecture of DeepSpeech. This talk might get a little bit technical, but just bear with me for first half of the talk. In the second half, I'll show you how you can actually just use this. So a little bit about me, that's kind of me in a nutshell. I'm a graduate student at Rice University. I also work with Mozilla mixed reality team, not the DeepSpeech team. And I'm a Google developer expert, Mozilla tech speaker. I've also worked with IBM TJ Watson and Almaden Research Labs before. So this is kind of our agenda for today. I'm going to talk about mostly the architecture, which is the DeepSpeech architecture, the CTC algorithms, the language model, and performance. Among all these four, I'm going to gloss over the CTC algorithm because this talk initially was for a 1 hour talk, but I have everything in the slide and this will be public, so you can go and see those slides, what are there, and if you have a question, just revert back to me. But I won't have time to go through the CTC algorithm today. Then I'm going to talk a little bit about the performance improvements you can do in that and what we are considering. I'll talk about mostly the network variants, not again the CTC variant because it will take a lot of time. Then we're going to talk about the data source, where you can train these, how we train that. So as you know, machine learning is as powerful as your source of data and how you can train on them. So how did we get even these data? And if you want to do it in your own language, maybe in Hindi or maybe in Bengali, or any language, how you can use the same system, how can you build models and use that. And I'm going to talk a little bit about the future directions we might take and what can be improved. So first, the core architecture. So DeepSpeech architecture is divided into a couple of things, mostly 5 layers. If you look at it, it's the softmax layer, the feed-forward layer, the bidirectional RNN layer, and the input features. So what it happens is that it basically takes some, okay, I'll just look at here. It basically takes some input features and then the feed-forward layer coefficients, and after that it's the 3 feed-forward layers. And then 1 bidirectional recurrent neural network layer, and then we have the CTC layer. What all of these does, first we'll talk about a little bit about the speech recognition features, because what we take is we take input speech. We have, since you can think of it as a sequence of values, for right now it works for 16-bit audio, so in here we take 16-bit audio at 16 kilohertz. So if we are going to transcribe MP3 maybe or something, you can use FFmpeg to convert it to a 16-bit audio. And then essentially what we do is that we guess for every 25 millisecond what is in that audio. Then we take a 10-second rolling window and keep on guessing that. Now that 10 millisecond window we are taking, every time we take that 10 millisecond window, we discard the previous output what we are getting. Essentially, what happens in a longer sentence is that every time you say something, once we have those words, we try to guess that and we move forward. The advantages and disadvantages of this is that when you try to use DeepSpeech for a longer text, for example, if I try to transcribe what I'm saying here today, it will probably give you a lot of errors. There are ways to deal with that, and I will talk about that also in later. So coming to the feed-forward layer, in these 3 layers, there actually is really a simple 3-4 forward layer with a width of 2048. And the redo cells basically means they are not interactive at all. So basically what it happens that so the ReLU cells they take it and they clip the audio. The clipped audio then gets inputted to the feed-forward layer, and then it works on that. So to do a clipping, the real I missed something in the slide. So the ReLU clipped at 20. I said the value 20, but I never described what it does. So this is the DeepSpeech architecture is actually built on a research paper by Baidu, and this is optimization parameter they came out with. We didn't really play with DeepSpeech, the 20 parameter, and for English, for our corpus, this works well. So you can, so if you want to implement in your language, it might act differently. So the bidirectional layer, instead of a single layer, we take this because it's computationally very intensive to train these, and it takes a huge computation power. So we take a single layer and we work with that. So the feed-forward layer is essentially exactly same as what we talked, and it does the same things. The softmax layer is pretty simple, but I need to tell you what the outputs are here. So it's in the essentially work as a more like if you have a particular alphabet like A to Z, and it's plus a space. For example, that you could be anything like I am talking. So this space. The softmax layer doesn't output just probabilities for those particulars, but it also takes the letters and alphabets what actually there, and extra thing you add into the blanks, which is actually required for the CTC algorithm to work. Here I'll just okay. Since I have hidden those slides, anyway, so after this, you have an explanation of how the CTC algorithm works, and essentially what it does is that it takes the previous input and it improves on top of that, so that the next probability you have, it gets better. It's a very crude explanation of what goes on, and you should just see the slide and learn that, but I need to tell you that so that you understand what happens in the language model. So when you go to the language model, first, we talk slightly about what we define as language model. When I mention the language model, really you can think about it. I have a sequence of labels, sort of think about the sequence of characters you know, and for each one of that sequence, the characters I can find kind of like are the probabilities. The basic says it's high, that means it has a higher probability. The character corresponds to a more chances of being in the dictionary. And the particular language we are talking about, so and the probability is low if it doesn't correspond to that specific dictionary. Now, for the loss function, we considered 3 models, and I'm going to talk a little bit about each of these because it starts with trial and error about which one was easier to do, and then we kind of tinkered with it and went forward. So first thing kind of like is the most naive version of the same. So what we are talking about before, the neural network plus the CTC algorithm, it allows you to get a probability for a particular labeling and for condition upon the acoustics input to the neural network. And essentially the naive way was, the first thing you say that I'm going to take this probability I get from the internal network condition and for this acoustic information and multiply it by the probability for this particular sequence of characters. According to the language model here, that's kind of like our version 1 of what we try to do. And the second one, what we try to do is that you could do essentially you could do the same thing, but then introduce another penalty term. What you do in this case is typically basically serve kind of 2 variables. You can call it alpha and beta, and it kind of weights the alpha and beta weights and these 2 other terms in particularly alpha weights how much important the language model is to the entire system, and beta pretty simply essentially tells that all that is that it is not really important, and what you are saying does not corresponds to the language I have. For example, a cat is running and a mat is running. Here, the beta will tell that okay, the second one is probably not corresponds to my language, even though it's you say that it has a high probability of being right. So it means like it's the value of that in the number of words in this particular sequence of this character. In particular, we just define words as some non-space character in a space. So we are basically counting the number of words there is, and basically the idea that is so low, you can sort of have one control over how important the language model is. So as you can see here, in version 3, what we did was that we took the same concept and the same penalty, and we kind of tried to restrict it using the third term. In particular, we introduced something third term, which is the particular loss of integrating the language from model. Basically, this final term is almost like the term before it counts the number of words in particular leveling, but it only counts the words if it is seen it, if it knows those words before. Otherwise, so it basically looks into a dictionary and it tries to see if those words are already there. Otherwise, it just discards and the ranking goes down. So we have basically some huge vocabulary to make it work, hundreds of thousands of words, which we made using 3 corpuses. I'm going to talk about it a little bit. And if it hasn't seen that before, so it's sort of knows that known words a little bit more, and more weightage is assigned to them. And if it hasn't seen the word, the weight just goes down. So basically what here happens is that the alpha model just says that the more words you have, the more sentence, the bigger you have and it makes sense, then yeah, go ahead. And beta literally just goes through that and says that okay, these words I have not seen, so just take the weight down. So in terms of actually these hyperparameters, just to give you a feeling for like how they have values, these ideas, so they are highly optimized for these specific purposes. So okay, so I'm going to talk about this, but this you have to go to the CTC algorithm to learn more. So when using these particular values you have now, I mean you can see that they're kind of, I guess it's took and beta prime kind of like it beta is basically saying don't be too wordy, and beta prime and space is saying only be wordy if you know what you are talking about. So which essentially means the words has to come from the vocabulary. More or less the interpretation of these take their parameters, and then again for grammar essentially it tells us how important the probabilities from the language model are relative to the rest of the system. And yeah, and let's talk about the performance. And so that brings us to the second part of the talk. How did we achieve, or did we even achieve near human performance with these optimizations? So our training data was 3. I should have a better slide. So our training data was from these 3 libraries. So we used TED's audiobooks, which we have around 2,000 hours of audio. So these are from TED.com. You can just go there and you download the audiobooks and you can convert them, use that. We also use the Fisher database. This is not free database. So they have kind of they have a system where they pay people to actually talk with each other, and they record that, and it's a very controlled environment, and then you can have those data sets for use. That's another 2,000 hours. So LibriVox, that is a website where you can, it's an open source website where you can just go and kind of read, have audiobooks. So imagine kind of like Audible in open source world. So people go there, voluntarily read Gutenberg books, and you have a site where you can download those audios and the corresponding book. So you can have a very good set of controlled data where you know what is being spoken about. But this is not a conversation, this is mostly reading a book. So the future architectural variants and what we can change with that. So there are two variants we can change. We can talk about that, the network variant and CDC. Today we are going to talk about the network variants. So architectural variants is actually, I guess, a bunch of a current system kind. DeepSpeech is basically you see two architecture in the input feature. Look more or less same. You have the same spectrogram for FCC, and instead of having the first few layers, instead of being just the feed-forward layers, and normally one thinks that the convolution layers in terms of, let's say, more image-based system. Whereas what we are doing at least a particular branch. You think we're about the time have the direction. We can talk about the FCC or whatever you can do in future. So right now, instead of doing a bidirectional layer, we can change it with convolution layer. And once we do that, it should go down, a lot of the work should go down to the network layer. And eventually the goal is that once we have implemented all these features, the size of the system should go down where you can have it running in a Raspberry Pi or small systems. Right now, the training takes a huge amount of time in a big system, but even running it in a small device like mobile will take quite a few amount of time for transcribe. I am going to run it in my laptop and show you that for a 45-minute text, it still takes around 4 to 10 minutes for it to transcribe. But for small talks, it can transcribe mostly instantly. So before I go to the speech corpora, I just wanted to So I have installed DeepSpeech here. Installing DeepSpeech is as easy as just doing pip install DeepSpeech, not that. So it's as easy as this. You should have a Python 3 running, and this will install DeepSpeech in your system. And I have already done that. And if I want to run it, so this is kind of, this is a pre-trained model. You can just go to the website, it will already have these models ready. And if you just want it running in English, this should be enough. But if you want to train it in your language, you have to do it. How you gain the data, I'm talking about how you actually build your own corpora after this. So for example, this is a tape talk, I'm going to try this. I have 4 minutes, so I'm going to start it. And it started. While it's doing its work, I'll go back. So to collect this data and to train it, we needed to actually use volunteers to actually collect this data, because the sources we had were LibriVox and VoxForge. None of them were huge enough to actually train your new model. I'll give you an example. If you want to right now train a new model for your own language, a good model should take around 20,000 hours of talk, conversation, and you can kind of make something work equivalent to what we have in TED. Actually, I think not on TED won't work, maybe something around a combination of LibriVox and VoxForce. So around 2000 hours of data should get you a good enough model, but not very good. So here comes the project Common Voice, and if you have been hearing about different activities in Mozilla community, there has been huge push on this. So what Common Voice is, this is a website and this is an open source project where you have a website and people can just go and you have sentences, volunteers can just go and read those sentences. Those are all tagged and annotated so that you can use those data to train. What it enables us to do is that it enables us to encounter for different kind of accents as well. The problem with the existing dataset is that the TED or LibriVox and the VoxForge, all of them, the problem is that we have a very limited demography of people who kind of contributed to that, and the English speaking demography is pretty huge. We have different accents, different way of pronouncing words, and the same model won't work as efficiently for all of them. For example, if I talk right now, record it and run it through DeepSpeech, it will probably give some error. I tried it yesterday night, it was more than the perfect 6.4% we normally get from this kind of data. So to make it improved, we need a project like Common Voice. Another reason I'm talking about Common Voice is that you can use Common Voice today, host it in your own server, or just use that for your own language and collect data to train. So some of the future directions. So right now it's still not really feature production ready. So you can, even though right now it's packaged in Python, you can just pip install. Once you try to actually train it and run it in within GPU specific TensorFlow versions, there are huge dependencies on where it can run and where it cannot. There is a Mozilla Discourse channel where you can just go and post your queries on the build problems you might get, and you will get quite a few. And one of the feature direction is make it more developer friendly, where you can just use it or use it to train or just deploy it in your own system, make it easier for developers. One of the optimizations we need were network quantization, which should allow us to make it small enough to run or lightweight enough to run in devices like Raspberry Pi, which even now is quite a bit of problem, the amount of time it takes. Other languages are problematic because we don't have a sufficient data source for that. Not only that, the present model, even though theoretically it should work for all the languages, you need to change a few things to make it work. There is a nice tutorial in Mozilla Discourse where somebody trained it on French language and how they did it, what are the changes they had to do, and even then they could only do it for their own voice. Which works nice if you want to build something like a voice assistant, but not sending your data to the cloud. So that should be a pretty good scenario, but how is it useful if it only responds to you? Maybe that can be a security feature. And so these are the kind of future directions we might take. This is the demo if my other demo doesn't work. So that is the source, what was spoken, and this is how it tries to determine the sentence. And while it's doing that, let's see what the real one is doing. In that case, I'll just stop it. Oh, I do have a smaller audio exactly for this reason. So this was what was in the audio. Can you read it? So as you can see, it took around this much amount of time to transcribe the text, and this one is still going on. Oh, I stopped it. So the limitations right now is that if you have a bigger audio and if it is in different language, different format, you just need to change it to WAV file, PCM 16-bit audio, 16 kilohertz. FFmpeg should be sufficient enough, so that's what I did for the TED audio. I just downloaded that. It was in MP4, I think, and I just used that to convert it, and it works normally. So with that, I have 3 minutes, so if you have any questions. Yeah.
Hindi language to Sadri, Kho or Nagpuri languages. We were trying to develop a platform while using the artificial intelligence, machine learning, even deep learning is also whatever you have given lectures today, that also we are doing. So could you suggest us, like it would be a very tough to start with. So we are the really beginners, even though we have expertise with. So I need some specific focus from your end as a suggestion. This is not exactly a question. We want to fruitful suggestions to go ahead with. Thank you.
So if you want to convert from one language to another altogether, and will that be text or audio?
Both.
Okay. So in that case, so what we talked about today, DeepSpeech, it's just from audio to text, and even that is on very specific language because you need large corpora. So this won't be perfect fit for that, and I don't know even an open source project which will be perfect fit, but there are systems which will be able to do that. So for example, you can just use Google to actually do that. So a very hacky solution kind of to implement this as a proof of concept will be just use Google's Cloud API and get your text, or use IBM Watson. Both are pretty good. So take any language, transcribe it to a text, convert that using Translate, and then use text to speech to convert that to again speech. There have been people have been doing that for almost 2-3 years now. You can if you just search in Google typing universal translator, and there have been a lot of hackathons people have tried to do that, and it works pretty well for near real-time purposes. If you can afford to use cloud for transcription. Otherwise, the only kind of alternate is that so DeepSpeech does one part, for English at least. DeepSpeech does one part, and you can use things like Pocket Sphinx and other open source solutions, and even Microsoft, and there's something called Mycroft, which kind of integrates a lot of these. For example, it integrates DeepSpeech, Pocket Sphinx, all of these to kind of do the same thing. But you still need something to translate, and you still need something to do text to speech. So we actually have another project going on in Mozilla which does text to speech, but that's in very experimental stage, so I cannot really recommend that yet.